resonance and nuclear effects for neutrinos and nucleus. So please, 20 minutes.
Sure.
Thank you.
Okay. So in the morning, I didn't have time to talk about this, so this is left for this afternoon session. I talk about coherent single pion production using smaller dynamical model, the so-called Satori model. So first, let me briefly remind you of what the Satori model is like. This is a small prototype of dynamical coupled channel model that contains only pion channel. And for the resonance, this includes only delta. So it's only valid in the delta region up to, say, W equal at most 1.4 GeV. And here is a comparison of Satori model with argon data, Newton-induced pion production data. And the full result from the Satori model is given by the blue curve compared with data. And the comparison is pretty good. And another feature of Satori model is to include non-resonant mechanism. And the non-resonant mechanism is given by the green curves. This is small for this channel, but not so small for this channel. And actually, this non-resonant mechanism is dressing the delta to make it dress. So dressing of delta resonance is observed from this difference between blue and red. This is a dressing effect on delta resonance. This is a feature of Satori model. And this figure is also showing the non-resonant mechanism. And essentially, the difference between black and green is a contribution from the non-resonant mechanism in this model. This is a sorry, not explain this, but this is for electron spectrum for this process for a given Newton energy. I forgot how much Newton energy is used to calculate this exactly. Probably I think 1 GeV or something.
So the distortion in shape is the change in sign as you go across the peak of the resonance?
Are you talking about this?
Yeah, I'm trying to just understand
This means interference pattern changed as energy changed. Yes. Okay, so let me go on to the coherent pion production in delta region. The motivation of this working for coherent pion production is to understand the neutral current pi zero production that can fake the new appearance event. And also, there has been a report from experiment side that is rather puzzling, because no evidence for charged current reactions has been reported, while signature for neutral current event has been reported. This is opposite to the naive expectation, considering the isospin matrix elements. Naively thinking, we expect that charged current cross-section is about twice of neutral current, but the experimental situation is opposite. So this is puzzling. So that kind of situation encouraged lots of theorists to work on this. There are basically two theoretical approaches to coherent time production. One of them is based on PCAC, and the other one is based on dynamic couple channel, not necessarily couple channel, dynamic microscopic model. And in this talk, I talk about our model for coherent time production. Okay, for studying coherent time production, ingredient here is elementary amplitude from Satori model, and we also take care of nuclear medium effects on delta, namely mass and width can be different from the vacuum, and also delta can move in the nuclear medium that creates the non-locality. Also, emitted pion scatters again with nucleus to create final state interaction. These nuclear effects are taken care of by using delta Hall model. Okay.
Can
Yeah.
I make a comment? And I'm running ahead. I'm sorry, but when you mention the non-locality in the delta, you're actually putting non-locality in the kinetic term.
Yes,
Your
that's
delta self-energy has a local treatment. You have a local treatment of the delta in the medium. This is a function of the coordinate. It's fully local. I mean, you cannot do otherwise. You will have otherwise you would have to do some doorway analysis.
yes. Self-energy is local. Yeah.
And second thing, you're also to make your life possible, I would say, to do this. You're also linearizing on this non-locality. So you only take the leading effect on non-locality. So you make an expansion. It's not that you keep the non-local term in the denominator, but you make an expansion.
Yeah, that's not what we do.
Yeah.
Say okay. I mean, okay. This is a delta propagator in a vacuum.
Propagator, don't you?
What you?
Linearize the delta propagator.
No, we didn't.
Okay.
Okay, yeah, as Luis mentioned a little bit, but in the nuclear medium, we have Hamiltonian for delta that has kinetic energy of delta, and because the delta is bound in the nucleus, so this is a potential that delta feels, and also this is a potential of the other nucleons actually. And this kinetic term creates non-local effect. We don't expand this propagator with regards to this term. Actually, we simply integrate over momentum of delta. So, yeah, that's what I do. Yeah.
Can I read your sentence from your paper? Sorry.
Okay.
Sorry.
Please.
Before equation 22, we incorporate the recoil effects of the delta self-energy in the first order approximation. This is done by linearizing the delta propagation with the following equation, expansion. And it is shown some expansion of the delta propagator, linearizing the W dependence. Can you say something? Okay, I'm sorry, I didn't want to put you in. I didn't want to put you in.
Right?
But baby.
My only point here was that you're making some approximations, and I really think they do not matter. so much, because ultimately you have some free parameters in the optical potential which you tune to pion nucleus elastic scattering. That
Yeah.
was the bottom line of my comment.
Yeah,
Okay,
we do so.
Luis, you know that now you get me all excited.
Yeah, but actually all this was
Because
not
one
for
has to know
conservation,
that
but for you.
Luis, of course, does an approximation right from the start and then hopes it works, and it doesn't. So
It does work.
Okay.
Also this gentleman here does it for photo production. He gets the data right.
Okay. Fine, thank you. We'll take care of that later. Please go on.
Okay, let me think about it. I'll come back to you later. Okay. Also, as a nuclear effect, we consider power blocking because delta can decay pi n in medium, but low momentum nucleon is forbidden by power blocking. And also, this is the so-called spreading potential parameterized in this form. And this take care of higher order effect, such as two-particle, two-hole configuration, coming back to delta again. So the kind of higher order effect is parameterized in this form. And we have parameters, central and LS type. These are complex parameters to fit pion nucleus total and elastic scattering data. By taking this spin orbit type interaction, actually, previous people found that VC and VLS are almost independent of energy. That was a good finding. Okay, so this is about final state interaction. Starting point is the Pine T matrix from Satori model. Pine T matrix can be decomposed into non-resonant piece and dressed delta. Non-resonant piece contains, of course, a ladder sum of non-resonant potentials, and dressed delta contains any diagrams that contains the excitation delta. And this is a basic ingredient to put into the nucleus. In this way, we construct pion nucleus optical potential. We do not make any modification on non-resonant piece. All nuclear effects are carried by dressed delta. And this green represents the medium modification on delta. Essentially, this this change in the nuclear medium is represented by this green area. Okay, and this pion nucleus optical potential is iterated by solving Lippmann-Schwinger equation to get to pion nucleus T matrix. This is what I will do. First thing to do is to analyze pion nucleus data to fix our spreading potential. Spreading potential is only parameters in our model. And this is a total cross-section as a function of pion kinetic energy. And this red curve is our full result. That is fairly close to data. And this magenta is obtained by switching off the spreading potential. This is the effect of medium modification. And we also fitted differential cross-section of pi nucleus scattering. Differential cross-section is shown as a function of pion angle, and I show result for 3 different energies: 80, 180, 280, and the comparison is pretty good. In this way, all the nuclear effects in this model have been fixed. And within this setting, we are going to predict coherent pion production. As I showed in 2 slides before, our pion nucleus optical potential is graphically given in this way. And we, for coherent pion production, we also need gamma nucleus to pi nucleus potential for photoinduced coherent pion production. Satori model also has a potential on the single nucleon that are from non-resonant piece and bare delta piece. Sorry, this is not a potential. This is an amplitude, non-resonant amplitude and dressed delta amplitude. Sorry. And the same, exactly the same medium wave effect is applied to the dressed delta mechanism. So once we fix the medium wave effect on delta by analyzing pion nucleus interaction, then the same nuclear medium effect is applied here, and gamma nucleus and coherent pion production amplitude is calculated by these figures. Pion production followed by rescatterings, right? Okay, so here's our result for the prediction for coherent pion photoproduction on carbon-12. Differential cross-section is shown as a function of pion angle. This is the result for the photon energy of 290 MeV. Suppose we do not consider any medium effect on delta, I mean no spreading potential, and also no final state interaction, then we get this high peak shown by this brown curve. But in medium, delta mass and width have to be modified. So we consider spreading potential to get this magenta. And also final state interaction is taken account to get this red curve. So our prediction is in agreement with data pretty well after including all nuclear effects.
The nuclear wave function is taken from a shell model, or
what we need is only charge distribution, and because this is a coherent process, so both initial and final states are ground state nuclei. Yeah. So by taking matrix elements, then what we have is essentially the form factor of the nucleus.
But not when you do the non-locality, right, of the delta.
It's only taken into account in the delta propagation. Yeah. So in
but then you need the delta, so to say, at 2 different points, and therefore you need the wave function here and the wave function there, which is not density.
Yeah, that's the approximation we made.
This is the linearization and the fact that it's local.
Okay, fine. Then I'm with you, Luis. Then I'm sort of surprised now. I always thought you had done the non-locality correctly.
But the fact that delta moves in the nuclear medium is still taken account.
It has done the non-locality of the delta approximating, which is great. But I still think
But not yet the real thing.
the real thing, the real, I mean, there are approximations there. My impression is that it doesn't really matter. So he's doing some approximations. I don't know some of them. I don't know how.
Well, but
they
you
are.
know from the stuff we did once that it matters at least if you don't have pion interactions.
If you don't have pion
Then
interactions,
you have a factor of
it
2,
matters.
and all the rest is hand waving.
But the point is how much of it you get when you use the same model to describe pion nucleus, and you get your
Yeah.
parameters in the optical
Yeah.
potential
Yeah.
from the same model. So this is what he's doing.
Okay.
So he has
So-
his model with his approximate non-locality, but then there he goes in with the same model, fits pion nucleon scattering. He goes back to photo production, and it is there. Now that
I think
gentleman over
Luis,
there.
I'm sorry, we're
Celine-
gonna have to,
sorry, okay.
we're gonna have to continue. Go ahead.
Okay. Yeah, still approximately, but yeah, still our treatment is something more than other people did. Yeah, okay. And this is this blue curve is obtained with only delta contribution. So this difference between red and blue is due to the non-resonant mechanism. This character is also different from other groups' calculation. Other group also, some groups considered non-resonant mechanism, but in their case, contribution was pretty small. Okay, so we made a parameter-free prediction for this case, and because photon data is pretty precise, so it is a very good testing ground for the model. So by this comparison, we passed an important check of our model, we believe. Okay, so we can now move on to charged current coherent pion production on carbon-12. This is a result for Newton energy of 1 GeV on the left-hand side, and 0.5 GeV on the right-hand side. This is a pion momentum distribution. Again, we are I'm now showing a similar figure as in the previous page. All nuclear effects are removed. Then we get this brown, and by taking out the spreading potential and finance interaction to get this red curve. So nuclear effect is very important to get the cross section right. There's no comparison with data for this particular quantity, but by comparison with photon data, we are pretty confident about this. And for lower energy side, this non-resonant mechanism looks pretty important. 32% increase due to the non-resonant mechanism. This is a different feature from the other calculations. And this is what I said. Okay, about non-locality. Oh, Uri he has gone. This is what Uri he always emphasized, and he and Tina Leitner pointed out this point of at first. So we take care of delta propagation by meaning that we included delta kinetic term in the delta propagation. And we here compare the result with and without non-local effect. And this blue curve this is for free delta. So 50% reduction is observed as a result of non-locality. And this blue curve is actually almost the same as what Tina and Ulrich found. So I'm not pretty sure Ulrich, what Ulrich had done, but yeah, our result and his almost the same actually. So we did almost the same thing, I think. Okay, but anyway, what we did more is that this large effect of non-locality persists even in the full calculation. This is what they didn't. And this red curve is a full calculation, so still an importance of non-locality persists. So yeah, considering the importance of non-locality, yeah, it's of course better to take into account explicitly. Yeah, other people partially took care of this effect by fitting pion nucleus data, and of course we fitted data too. Yeah, but yeah, we did something more than that. Okay, for comparison with data, let me show only one.
Yeah, please, just one.
But some other old data also exist, but this is a pretty new one. It's from I think Miniboom about ratio of charge current and neutral current coherent pion production cross section. What they found is 0.14, and all theoretical calculations give this ratio between 1 and 2. Sorry, thank you for that. Okay. And yeah, many theorists pointed out that this discrepancy may be due to the use of Ryan-Segal model of coherent pion production in their analysis. In particular, experimentalists use eta defined by this quantity to break degeneracy of several pion production data. But for this eta distribution, what most theoretical calculation gives by red curve, this is ours, are rather different from what the experimenters used, shown by blue curve. So this large difference could be a reason for overestimation of neutral current cross section. Okay, yeah, that's it. Thank you for your attention.
All right, we don't have time for a lot of questions. There was discussion during the talk, so why don't we just immediately go to Sergey?
Okay. Yeah, you're welcome.